Hello, good day. Today we shall be looking at the last past paper, October November 9702, paper 4, variance 1, October November 2023. And let's look at the first question. Uh, let's look at the first question. And the first question is state what is indicated by the direction of gravitational field line at a point in a gravitational field. State what is indicated, the direction of gravitational field line. Now, what is gravitational field line? Let me quickly explain it. The Earth is spherical, assumed to be spherical. The gravitational field line around the Earth is radial and it's always inward. It's inward like this. The gravitational field line around the Earth is inward. It means that any object placed around this line, any mass placed around this line, will be attracted toward the center of the Earth. Let's say this is mass. So any object or mass placed around this mass will be attracted toward the center of the Earth. So what does this mean? It simply means that the line, the question asks us, the line, the direction of the line, what does it mean? The direction of the line, the arrow inward, simply means or is the direction of the force, is the direction of the force on a mass placed, the force on a mass placed in a gravitational field. If you remember, that mass accelerated towards the center by the gravitational force pulling it toward the center, which is also the direction of the line. So the line F-I-E-L-D. So the line indicates the direction of force on the mass placed in the gravitational field. That's the meaning of the line. The second question, explain with reference to gravitational field line why gravitational field near surface of the Earth is approximately constant for small changes in height. So this is the meaning. The question asks us to explain why gravitational field line near the surface of the Earth is approximately constant for just small changes in height. Now, what's the formula for gravitational field? G. The formula for gravitational field is Gn over radius squared. Now, this is Earth. Now, if another body moves, okay, let me draw something bigger here so I can explain it properly. Now, this is the Earth. Going to write E. This is the Earth. The radius of the Earth is R, big R. This is the center of the Earth. When a mass moves from here and move a bit higher, small distance. So what the question is asking us is that Explain with reference of gravitational field line why the gravitational field near the surface of the Earth is approximately constant for small change in height. For small change in height. Remember that gravitational field is Gm over r squared, and r is the radius of the Earth. It's around 6.4 times 10 to the power 6. Now, for a body above the Earth, h above the Earth, the gravitational field can be, you have to consider the distance from the center, r plus h all squared. Now the question is telling us that what's the reason why the gravitational field at height above the Earth is approximately the same as g. And the reason is that for small change, for small height, such that the height is far less than the radius. For example, now, if we had 1 plus 2 million or 20 million, it's like 2 million and 1. The 1 is really insignificant, it doesn't change 2 million. So the same thing with this context. Since h is far less than r, so h plus r will be approximately equal to r. It's just like saying 0.1 plus 6.4 times 10 to the power 6. 0.1 plus radius of the Earth is approximately equal to radius of the Earth. So now the explanation will be, now the gravitational field near the Earth surface is approximately constant for small change in height. And I'm going to put it like this: the change in height, delta h, near the surface of the Earth, is extremely small. Compared to the radius of the Earth, 6.4 times 10 to the power 6. So the field line are approximately the same as 1 on the surface of the Earth. That's the reason. I believe it's clear. Now the next question. A large isolated uniform sphere has a mass m. As you can see, the sphere has a mass m and the radius r. Point P lies on the straight line. You can see point P lies on the straight line at a particular distance x away from the center of the sphere. If you can see, it's at a distance x from the center of the sphere. And they said variable displacement, it means the distance is changing. Show that the variation with x of the gravitational field strength. This graph is showing the graph of gravitational field strength at a point P due to the sphere for the value of x, where P is inside the sphere. Now the magnitude of gravitational field at the surface of the sphere, gravitational field G at the surface of the the surface of the sphere, at the surface of the sphere, not away from the sphere, surface of the sphere. You see that the surface of the sphere, the gravitational field is Gm over radius, because the distance from center to surface is radius. So the gravitational field strength at the surface of the Earth sphere will be this. So the question asks us, determine an expression for y in terms of m and r, and identify any other symbol used. Okay, that's what we just said now. So y is the gravitational field at the surface of the sphere. At the surface of the sphere, the distance is the radius of the Earth. Now, if you remember previously, they mentioned m as the mass of the sphere, r is the radius of the sphere. They never mentioned g. That is the other symbol that we use. G is called gravitational constant. Gravitational constant. The value is 6.67 times 10 to the power of negative 11 Newton. I think it's always given in the first page. This is it here, Newton meter square per kilogram square. Newton meter square per kilogram square. That's what they ask. Now explain why at the surface of the sphere, G always has opposite sign. Now, at the surface of the sphere, G always has opposite sign. Let me go back to my diagram. The distance, the radius of the sphere is from center to the surface of the sphere. It's increasing. As we are going up, it's increasing. And don't forget that the gravitational field line, the gravitational field line is inward. And the first question they asked us was, what is the meaning of the direction of this field line? We told them that the direction of gravitational force on a mass placed in the gravitational field. So, which means that the direction of force is increasing downward like this. Force is downward, but the distance, as force is coming down, remember you are closing in on the radius of the Earth, so which means the distance is decreasing. So force and distance are in opposite direction. Distance increase opposite to direction of force. As the force is increasing, you are closing as the mass is coming closer to the Earth's surface, the distance is decreasing. At the same time, the distance increase upward, force increase downward. So which means that the gravitational force or force, number one, force is in opposite direction. Force is in opposite direction to displacement. X. Force increase downward, like, okay, I don't want to mess up the first solution. Force increase downward, distance increase upward. They're in opposite direction to each other. That's why it's negative. It's 2 marks, 2 points. Another point is that number 2, gravitational force is always attractive. Gravitational force is always attractive. Attraction can only take place when one body is positive, the other is negative. The opposite polarity attracts, same polarity repel. So, simple explanation. Let's do the next question. Next question is to complete figure 1.2 to show figure 1.2 to show the variation of g against x up to the value of plus or minus 3r, which point P is outside the sphere. Let's see the figure. Oh, this figure. Now, g against r. You know, we all know that inside the earth, from the center of the earth to the surface of the earth, gravitational field is constant, or gravitational field strength G is constant, 9.8, from the center of the earth to the surface of the earth. So, center of the earth is 0 here, this is it, and from center to surface is between 0 and r. So let me use another color so to be clear. Okay, blue. Let's see. Yeah, this is negative r. Center of the earth to the surface of the earth is constant. You can also use this place too. This is center of the earth to the surface from 0 to r. From 0 to r is constant. From 0 to r is constant. Now what happens when the body is moving outside the surface of the earth? At r it is y or g. Let's see at 0.5. Now, since the body is gradually moving away from the surface of the earth is r. At 2r, we are moving away from the surface of the earth. So I have a formula to calculate gravitational field outside the surface of the earth. Gravitational field outside the surface of the earth can be calculated using radius of the earth square over the radius outside the surface of the earth multiplied by gravitational field at the surface of the earth. So at 2r outside the surface of the earth, let's find the gravitational field. The radius of the earth in this context is big R all square, or negative big L. It's cancelled out. Okay, let me do it. Negative big L square. This is square. The radius at the surface of outside this earth in this case is minus 2r all square multiplied by g, gravitational field at the surface of the earth. At the end of the day, we have r square over 4r square multiplied by g. This cancels this. At the end of the day, we have 0.25 g. So when the radius is 2r, the gravitational field is 0.25. 0.25 should be between 0 and 0.5. That's half of it, somewhere here. So let's find the radius when it's negative 3r. The same method. Remember that the radius at the surface of the earth is negative r. Now at 3r, negative 3r squared multiplied by g using the same formula. So we have r squared over 9r squared multiplied by g. This cancels this. We have 1 over 9. 1 over 9 is 0.11 g. 0.11 is kind of close to this. Okay, I think somewhere here. At the end of the day, we have this kind of yeah. Same thing here too. 0.25 should be here. Somewhere here. 0.11 is there. So we have something like this on the other side. Yeah. This is the graph. This is what the question is asking us to complete. I believe it's clear. Let's move to the next one. Now the next question, we are asked to define specific heat capacity. Specific heat capacity. Now what is specific heat capacity? Okay, let me write now the formula out. Quantity of heat energy supply is always MC, change in temperature. M is the mass, Q is the quantity of heat, change in temperature. C is the specific capacity. And you make specific capacity structure formula, we have quantity of heat over mass times change in temperature. You can use this formula to define specific heat capacity. The amount of heat energy or thermal energy needed to raise the temperature of a unit mass. To raise the temperature of a unit mass by 1 Kelvin without going through a change of state or phase. It can also be the energy per unit mass. Energy per unit mass to change energy per unit mass. Okay, per unit change in temperature. Okay, we can also do it like that. How many mass? Okay, if you are going to use the formula, let's do it like this. Okay, so let me use this. The amount of heat energy or thermal energy needed to raise the temperature of a mass by 1 Kelvin. Let me say unit mass by 1 Kelvin without going through a change of state or change of phase. It can also be if you use the formula, the quantity of heat energy needed per unit change in temperature and energy per unit mass is also acceptable. Don't forget to put the unit. I like putting the unit when I'm defining it. SI unit of specific capacity is joule per kg per Kelvin. That's it. The next question. An ideal gas of mass 0.35 kg. The mass is 0.35 kg. Is heated at a constant pressure. Isobaric The pressure is 2 times 10 raised to the power 5 Pascal, so that the internal energy increases by 7,600. So during the process, the volume of the gas increases from V1 to V2, and the temperature increases by 56 degrees Celsius. The first question: show that work done on the gas. The formula for work done is P dV, that is pressure times change in volume. The pressure is 2 times 10 raised to the power 5. Volume V2 minus V1, 0.063 minus 0.038. And use a calculator, so we have 5,000 joule. 1 mark. State whether the work done on the gas is positive or negative. Since the gas is expanding, from small volume to higher volume. Since the gas is expanding, the work done by the gas, work is done by the gas, because the gas is pushing the system. The work done by the gas, work is done since the gas is expanding. Okay, let me do it like this. Since the gas is expanding, hence work is done by the gas. Therefore, work done is negative. If it's assuming work is done on the gas, work done will be positive. Determine the magnitude of the thermal energy Q transfer. So from first law of thermodynamics, change in internal energy is heat supply plus work done on the gas. So it's plus because it's work done on the gas. It's negative is work done by the gas. So in this case, the question, if you remember, its internal energy increases by 7,600. That's change in internal energy. We are looking for heat supply. The work done given is 5,000 joule. Remember, work is done by the gas, negative. So hence, Q is 7,600 plus 5,000. So which is 12,600. So that's work done. That's heat transfer to the gas. Heat supply to the gas, heat transfer to the gas, positive. Next one. Calculate the specific heat capacity of the gas for this process. Give the unit. I did that earlier. Unit for specific capacity, joule per kg per Kelvin. Specific capacity, I gave you this formula earlier. It's equal to C Q over M, change in temperature. The heat is 12,600. The mass of the gas, I think we are given earlier, 0.35. And change in temperature is 56 degrees Celsius. Mass 0.35. Remember that Kelvin does not affect change in temperature. 56. So from here, punch your calculator, 12,600 divided by the product of 0.35 times 56, then you get 640. the gas in B is now heated at a constant volume rather than constant pressure. It's heated at a constant volume rather than constant pressure. So this question said the gas in B is now at constant, is heated at constant volume rather than constant pressure. So the increase in internal energy remains the same. Okay, now constant volume, that process is called isochoric. Constant pressure, the process is called isobaric. Remember, the gas is now heated at constant volume. Okay, from that statement, work done is P to V. If the volume is constant, then there's no work done. That's the first point. So I'm going to write, since there is no change in volume, hence no work done. No work done. And the question also said that the increase in internal energy of the gas remains the same. The increase in internal energy remains the same. Since the increase in internal energy remains the same, if you remember, change in internal energy can be 3/2 K change in temperature, translation kinetic energy. So internal energy is a function of change in temperature. So if there's increase in internal energy, there will be increase in temperature. If it's the same, the temperature is the same. So same gain in internal energy. Same gain in internal energy simply means same change in temperature. Now, but the question now asks us that use the first law of thermodynamics to state whether the specific capacity of the gas for this process is less than the first term, same as the first term, or greater than the first term. Now, the key to this question is the same temperature. However, to produce same temperature, same temperature change, same temperature for a particular material, to produce same temperature for a particular material, lower specific heat capacity is needed. That's a point. Because material with lower specific heat capacity can efficiently absorb and store more thermal energy. So when a material has a lower specific capacity, let me explain. It means that it requires less energy to produce the same temperature change compared to a material with higher specific capacity. This is because material with lower specific capacity can more efficiently absorb and store energy. That's just the key. A material with lower specific capacity requires less energy. So to produce the same temperature change compared to material with higher specific capacity because it can store and absorb thermal energy efficiently. That's it. Number 3 question. N in this equation means number of gas molecules. Number of gas molecules. N is mass, that small m is mass of one molecule. Mass of one molecule. Y, this stuff means mean square. It means mean square speed of the molecule. Mean square speed of the molecule. That's it. The next question. Use the equation of state of an ideal gas. The equation of state of an ideal gas to show that the average translational kinetic energy of the molecule of gas at thermodynamic temperature T is given by this. Now since PV equal to NKT and also PV is also equal to 1 over 3 NN, that's the equation of ideal gas. So equation 2, equate both of them. When you equate both of them, we have NKT equal to 1 over 3 NN C squared. So big N cancel big N. So we have when you cross multiply, we're going to have 3KT equal to NC squared. Multiply both sides by half. So we have 3 over 2KT equal to half MC squared. So hence 3 over 2KT equal to half MC squared is translation kinetic energy. That's the proof. EK. Next question. The surface of a star consists mainly of a gas that we assume to be ideal. The molecule of the gas have a root mean square. This is root mean square of 9,300. So it means this is root mean square. Root mean square. This is written of 9,300. So which means that mean square is 9,300 raised to the power 2 when square goes that remaining. So the mass of the molecule of the gas is this. determine degree SF, the temperature of the star. Okay, we call that translation kinetic energy, what you just proved now, is 3 over 2 kT. And along the line, we encounter something like this. That's a kinetic energy, which is 3 over 2 kT. So we have the mass of the molecule is 3.34 times 10 to the power of negative 27. Mean square speed is 9,300 square. So equal 3 over 2 kT. K is Boltzmann constant. Is in front of the beginning of this paper, or the constant. 1.38 times 10 to negative 23 T. So from here we have okay, 1 over 2 times 3.34 times 10 to negative 27 multiplied by 9,300 square equal to 3 over 2 is 1.5 times 1.38 times 10 to negative 23 T. Make T the subject of formula. So T is half of 3.34 times 10 to negative 27 multiplied by 9,300 square divided by 1.5 times 1.38 times 10 to negative 23. Punch it in your calculator. It should give us 6,000. Okay. C question. Radiant flux intensity of radiation. Radiant flux intensity is from the star is given as this. Radiant flux F when the observed distance is this. Observed distance D. Calculate the luminosity of star. The formula for luminosity is radiant flux multiplied by 4 pi d squared. So luminosity radiant flux is 2.52 times 10 to negative 8 multiplied by 4 pi. YD is 4.16 times 10 to 16 all square. So punch this in your calculator. L will give us 5.48 times 10 to 26. 5.48 times 10 to the power of 26. The unit of radiant flux, sorry, the luminosity is watt. Now the next question, determine the radius of the star. Determine the radius of the star. So in this case, we're going to apply Stefan Boltzmann law, which is luminosity L 4 pi Stefan constant radius square temperature is about 4. So we are looking for radius. So the radius is the luminosity L over 4 pi Stefan constant temperature is about 4, which will be square root to find the radius. So the radius will be L is what we obtained previously, 5.48 times 10 to the power of 26 4 pi is a constant. Stefan Boltzmann's constant is 5.67. In the front page of your question paper, multiply by 10 to negative 8. Multiply by the temperature. I think we got the temperature approximately 6,900. Yeah, the actual value for approximately down 6,980 raised to power 4. Let's crunch this in a calculator. Square root of 5.48 times 10 to 26 divided by 4 pi 5.67 times 10 to the negative 8 multiplied by 6,980. You can also use 6,900 to the power 4. So we have 5.69 times 10 to the power 8. The gas at the surface of a star has a very high pressure. Use basic assumption of kinetic theory to suggest why in practice a gas at the surface of the star is unlikely to behave as an ideal gas. So, which means that it has to go against kinetic theory model. So you have to invert kinetic theory model. One of them is, volume, the volume of molecule. Volume of molecule is not negligible. Not negligible. Compare with volume of the gas. So the other one is that the pressure here is extremely high. So molecules are close together. The pressure is extremely high. Extremely high. So molecules are close together. Meanwhile, the kinetic theory model is that volume, like my first one I said, volume of molecule not negligible compared with volume of the gas. If you remember on the kinetic theory model, the volume occupied by the gas molecule is negligible. Since the question said unlikely to behave as an ideal gas, so I inverted it. The volume of the molecule not negligible compared with the volume of the gas. And the second one, I said the pressure is extremely high, so molecules are close together. The molecules are not supposed to close together. If you remember, one of the kinetic theory model is that intermolecular forces of attraction are negligible. Why? If particles attract each other over a long distance, what will happen? They will tend to clump together in the middle of the container. So the particle travel in a straight line between collision. Remember that the first model is gaseous molecules are in continuous random motion. So if pressure is if the molecules are close together, they will move in a straight line. They will disobey the first one that said gaseous molecules are in continuous motion. So I negated two out of the laws. One that said volume is negligible compared to volume of that said not negligible. The one that said gaseous molecules are in random motion. I have to negate it that since the pressure here is actually high, they come together, they eventually move straight line. Let's move to the next one. Simple harmonic motion. A heavy metal sphere of mass 0.18 kg suspended from a string. The sphere is undergoing oscillation from side to side as shown. The oscillation of the sphere may be considered to be SHM with amplitude 0.36 and period 3 seconds. The first question, state what is meant by simple harmonic motion. Okay, let's make it simple. Like what they said, simple harmonic motion. 2 marks at I prefer sorry, like I said, simple harmonic motion is a motion in which the acceleration is proportional. The acceleration is proportional but opposite. Proportional but opposite in direction. Opposite in direction. Opposite in direction to the displacement. Displacement x from a fixed point. Fixed point or equilibrium position or undisturbed position. That's it. Next question. Calculate angular frequency F. Okay. Angular frequency radian per second. That's W equal to 2 pi f, and f is 1 over period, which is 2 pi over t. On the question, we are given period to be 3 seconds. So 2 pi divided by 3, that will be 2.1 radian per second. Next question. Total energy of the oscillation. Energy of a simple harmonic motion, energy is constant, the total energy is half Ka squared, where K is mW squared. So total energy is half mW squared squared. So our total energy will be half the mass 0.81 kg was given earlier. Omega, we just got it now, W 2.1 square. Amplitude 0.036 square. So punch it in your calculator, it's going to give us 2.3 times 10 to negative 3 joule. The suspended sphere is now lower into water. That's damping. The sphere is lower into water. That's damping. So the sphere is given to a sideways displacement. It's given a sideways displacement from equilibrium position sideways. Then released. The water causes the motion to be critically down. Remember, critically down does not oscillate. Critically down does not oscillate. It just will decrease down to zero. So stretch the variation of displacement of x on the given position from t equal to 0 to t equal to what? 6 seconds. Mm. Remember the amplitude is 0.036 positive. So 0.036 should be 1, 2, 3, 4. Let's see. 0.036 should be here. It's around this place, 0.036. 0.036. So the critically damped just decreased to 0 in the possible shortest time as possible. So the displacement of x of the sphere from its equilibrium position from t, so it's going to damp, critical damping, the amplitude will decrease without oscillating to 0 at the shortest possible time. Something like this. Yeah, something like this. At the shortest possible time. It never reach 6 seconds. It just decreases to 0 at the shortest possible time without oscillating. Okay, that's it. So starting from 0.036 amplitude should be a mark. The nature of the graph, decreasing gradient up to 0, 1 mark. Stopping at the shortest possible time, another mark. Number 5, electric field. Define electric potential. Electric potential at a point. Electric potential at a point. Okay, you can say work done. Work done on a unit positive charge on a unit positive charge bringing the unit positive charge from infinity to that point. Next question. Two isolated metal sphere X and Y situated near to each other in the vacuum with the centers 24 meters apart. The centers are 24 meters apart. When P is variable distance X from the center of point X of sphere X on the line joining the center of the sphere. So state 3 conclusion that can be drawn about the sphere, equal 5.1. Okay. Now, the electric potential against distance. So don't forget electric potential is a scalar quantity. Electric potential is a scalar quantity. So let's start like this. So let's, like I said, since electric potential is a scalar quantity, going to follow the way the graph goes. Since the electric potential is a scalar quantity, hence the charge on X is negative. You know why? Because it's on the negative region, this side, and the charge on Y is positive because it's on the positive axis up. So that's how scalar quantity behave. They follow wherever you place them. Another point is that when you check this space, charge of X from center to this place is constant. From center to this place is constant. That's the radius. So radius of sphere X is 2 meters. Let's check that of Y. Where is constant? The radius from 20 to 4. 24 is constant. So Y radius of sphere Y is 4 meters. The last one, so the last point, let's critically look at what we can see from here again. Okay. Now, when you check this diagram, you see that the potential from the center down here decreases to 0. The other one from 0 to this place, which means there's a point at which the potential is 0. So, so I can say that potential at X at that point at 12, potential at X, a potential of Y is equal to 0. So Vx equal to negative Vy. Now what's the formula for potential, electric potential? Q over 4 pi E naught X or R. The same thing with this, Q over 4 pi E naught R. So from here we have Q 4 pi E naught, cancel 4 pi E naught, so we have Qx over Rx equal to negative Qy over Ry. So when you check it, so the distance from center from 0 to here is 12. From the other one, 12 to 24 is also 12. So we have Qx over 12 equal to negative Qy over 12. 12 cancel 12. So the charges are equal to each other, but in opposite direction. So we can also say magnitude of charges on the sphere are equal. I say that. So these are the 3 conclusions I can see from here. Let's go to the next question. A positively charged particle is placed at the point P in B such that X is 12 meters. The particle is released. Describe and explain subsequent motion of the particle. A positive charge particle is placed at the point P such that x is 12 meter. Okay, where is point P? Such x is 12 meter. Okay, 12 meter. Okay, this is what they're trying to say. Now, this is x. This is x. This is y. Charge of x is positive, is negative. Y is positive. The particle P, 12 meter. That's a positive charge particle such that x is 12 meter. Okay. Let's say particle P is here and it's positive. So that particle will be attracted by the negative charge in this direction. And the same particle will be repelled by the positive charge, like pole repel. Will be repelled. So repelled by y toward this direction. Attracted by x, repelled by y, attracted by x. So in this case, so the particle is attracted to x. Let's play the particle will be attracted to x or repelled from y. Repelled from y. You can also say how many marks? 3 marks. You can also say, now this is the force of y, this is the force of x. Now the resultant force is in the direction of x. The total force is in the direction of x. So you can also say, or resultant force Fx and Fy on the particle is towards x or away from y. So since there is a resultant force, hence acceleration of the particle increases. Newton's second law of motion, F equal to ma. Increase in force, increase the acceleration. Next question. Define magnetic flux density. Magnetic flux density. F equal to BIL. B is magnetic flux density. Is F over IL. So I can say magnetic flux density. This is the force acting. This is the force acting per unit length on a conductor. Carrying current. On a conductor carrying current current perpendicular to a uniform magnetic field. A force carrying current on a conductor, the force acting per unit length on the conductor carrying current perpendicular to uniform magnetic field. Let's go to the next one. Electrons are moving in a vacuum. The speed of electron is 1.7 times 10 raised to the power 7. So the electron enter a uniform magnetic flux density. This is the magnetic flux density B. And show the path of electron. Look at the path of electron. The path of electron is direction of force, downward. Electron, the charge is negative. So state the direction, the path of the electron remains in the plane of the page. State the direction of magnetic field. Okay, like as you can see, the force is downward. You can see that path is direction of force is downward. So what is the direction of magnetic field? Since the force is downward, according to Fleming's left-hand rule, there's no way I can show you my hand right now, but according to Fleming's left-hand rule, the direction of magnetic field is into the page. Why is it into the page? Because okay, let me show you something. Into the page, the electron is going like this. Electron is negative. If the magnetic field, let's say, this is into the page, X into, and the electron is negative, it will go downward if it's into the page. Assuming it's proton, for proton into the page to go upward. That's how it works. So according to Fleming left-hand rule, it's into the page. Now show that the magnitude of force exerted on each electron of a magnetic field is 1.3 times 10 to the power 4. What is the magnitude of force on the electron in the magnetic field? The formula is dQV. The magnetic field, we are given 4.8 millitesla. Charge on electron is 1.6 times 10 to negative 19. Velocity is 1.7 times 10 to the power 7 as given earlier. So punch these in your calculator. We're going to have 1.3, 4.8. We have 1.3 times 10 to negative 14 newton. On figure 6.1, that's the previous figure. Draw an arrow to indicate the direction of centripetal acceleration. The direction of centripetal acceleration of the electron when it enters the magnetic field at point X. Direction of centripetal acceleration. So since the force is downward, it's like this. As if you're a circular path. It says you show the direction of centripetal. Draw an arrow to indicate the direction of centripetal acceleration. as acceleration is downward toward this is acceleration toward the center of the circle. Centripetal acceleration is downward, so that's it. So that's centripetal acceleration A AC. The next question: use information to calculate the distance d between the path of the electron entering the magnetic field and the path of the electron leaving it. Okay. Now in this context, in circular motion, centripetal force provides the magnetic force, and centripetal force is mv squared over r. Magnetic force is bqv. We are looking for the question asked us to find the distance d. So when you check this question, the distance d in this question is like the diameter. When you check it, don't mind my diagram. The distance d is diameter. So our diameter is 2r. So to get the diameter, we need to get the radius first. So let's find the radius here. So this cancels this. So we have mv equal to bqr. So the radius is nv over bq. So radius is called our mass. That's mass of the electron. It's constant 9.11 times 10 to negative 31. It's given in front page. Speed. The speed that will be 1.7 times 10 to the 7 all over magnetic field. That's 4. Oh, you don't need to do it in this way. You are still going to get it this way, but we have the magnetic force already. So I don't need to go through this context. Magnetic force is 1.3 times 10 to the power minus 14. So there's the reason why they asked us to find it before. So centripetal force is mv squared over r. Magnetic field is 1.3. Magnetic force is 1.3 times 10 to the 14. So so radius will be 1.3. From here, I'm looking for my radius. Let's cross multiply mv squared over r. So mv squared equal to 1.3 times 10 to the negative 14 r. So my radius will be mv squared. M is 9.11 times 10 to the power of negative 31. Velocity is 1.7 times 10 to the power 7 all squared all over 1.3 times 10 to the power of negative 14. So in this case, my radius give me a calculator 0.02, and we are looking for d. D is 2r, which will give us, so d is 2r, which is 2 times 0.02, that's 0.04. That's d. The next question: the electrons are replaced by positron. Positron is positive, not negative. Positrons are moving with the speed of 3.4 times 10 to the power 7. I think the bigger speed compared to 1.7. The bigger speed along the same path. Along with the same path. The question asks us to draw the positron enter the magnetic field at point X. So on the same diagram, draw a line to show the path of the positron through the magnetic field on the same diagram. So what we do is this. Remember the formula here Okay, remember this formula. Centripetal force equal to magnetic field. So NV squared over R equal to BQV. This cancels this. So NV equal to BQR. So radius is NV over BQ. Now, the question said the speed has changed now along the same initial path. So it's about radius and the speed. Radius is proportional to speed. So in that case, increase in radius will increase the what? Speed. So since the speed has changed, the radius will change. So radius equal to kb. K is radius over b. So we have r1 over v1 equal to r2 over v2. The first radius, I think we got 0.02, and the first speed 1.7 times 10 raised to 7. The second radius, I don't know, but the second speed is 3.4 times 10 raised to 7. First multiply, do your math. The second radius is 0.04. So the second diameter should be 2 times 0.04. The second diameter is 0.08. Remember that the first diameter is 0.04. Now, which means that this diameter, the new diameter, is twice the first diameter. So let's go back to the sketching. Let's go back to the sketching, which means, and this time around is positive. So for positive, oh, look at what I did before. When it's positive charge, what force? And what I did before, the force is upward. Can you see this? The force is upward. So now, so in this place, so it's from the same path. It's from the same path. The direction of force, according to Fleming left-hand rule, to move upward. Put the direction of force there, it's going to move upward. It's going to move upward. And the diameter is 2D. So from here to here is D. So the diameter is 2D, yeah, 2D vertically from X. This is what the question is asking us to do. The next one, number 7 question. A bearing current I through a resistor of resistance R in a circuit as shown. Look at the bearing current, block form. When look at the period is T. One period is T. We have a negative current and we have a positive current. So the current has a magnitude of 2I when it's positive direction and I naught when it's negative direction. So we have two currents. When it's positive, when it's positive is 2I. When it's negative, the current is I. So it's decreasing. When it's negative, it increases or double when it's positive. The period is T. Determine the expression for I naught and R for the power dissipated. The formula for power is I squared R. In negative direction, the current is negative I naught multiplied by R. Negative I naught squared will give us I naught squared. square R. Positive direction, the current is 2 I naught. 2 I naught squared multiplied by R will give us 4 I naught squared R. So the power in positive direction is 4 I naught squared R. The next one, sketch the graph between this 0 to 2t. Label the power axis. So sketch the graph of power between t equal to 0 and t equal to 2t. Label the power axis with appropriate scale. Okay. Now, remember that we have two currents, I naught. Now is now power. Okay. Power. We have first power is I naught squared R. Second power is 4I naught squared R. So in this case, the maximum current is 4I naught, and the minimum current is what? I naught. So it is square form. So I think we're going to do something like this. The square waveform. So I naught. Okay, let me do like this. So if this place is 2I naught, somewhere here, 1, 2, 3, 4. Let me somewhere here, 1, 2, 3, 4, 5. Here is I naught. This is 3I naught. And this is 4I naught. Now, the first graph, I naught is from 0 to negative I naught is from 0 to 0.5. So for power, you have square, it is now positive. So no negative from 0 to 0.5. And here, when it's 2I naught, in this case, when it's 2I naught, it's from 0.5 to 1. 2I naught is the one that forms 4I naught here, 0.5 to 1. And from 1 to 1.5, look at it here, from 1 to 1.5, negative I naught, the power, the negative is positive. So 1 to 1.5 is still on I naught. But from 1.5 to 2 is 4I naught. At the end of the day, we have this graph, the square waveform. The power has taken away the negative when you square the current. So this is the graph of power. So that's the graph. Oh, I have to put the square. The current is square. Like that. Against time. So again the period. So next question. Use the answer in B to determine the expression for I naught and R for the main power. Oh, for the main power. So the main power, that's the average power. The main power is always average of maximum power. So the main power, average of maximum power. In this case, we have two currents, so there will be two power, I naught squared R plus 4I naught squared R, so which gives us 5 average power is 5 over 2 I naught square R. The root mean square current. Now, the root mean square current, RMS square, is always the average current in the same resistor. That's 5 over 2 I naught square. This context. So from here, so root mean square current is square root of 5 over 2 I naught square, so which is square root of 5 over 2 I naught. Perfect. Number 8. Show that the momentum of a photon towards magnetic radiation is this. Now, energy of photons is usually HF, which is equal to hc over lambda, equation 1. From our Einstein equation, energy can also be mc squared. So you equate both e's together. So hc over lambda equal to mc squared. 1c cancel 1c. We have h over lambda. This mc is mass times velocity. So mass times velocity is momentum. So that is it. Momentum equal to h over lambda. So that's it. So if you show it, show that given by, so it show that the momentum of the radiation is given by P equal to h over lambda. Okay. Okay, alternatively, you can also look at it like this. Do you know that E equal to mc squared? You can amalgamate mc is momentum multiplied by c. So momentum can also be E over c. Like energy is momentum. Let me leave it like this. Energy can be Pc, and the other energy is hc over lambda. When you equate them together, I can have Pc equal to hc over lambda, c cancel c. So I have this again. I'm sorry. H over lambda. So alternatively, so this or use the expression here to show that a photon in free space has momentum of this. A photon in free space has the momentum of this is a photon of red light. Now, what is the wavelength of red light first? Red light is between 620 to 750 nanometer, which means you must get the value of this range as wavelength, so to be sure that it's red light. Since wavelength is Planck constant over momentum, our Planck constant here is 6.63 times 10 to the power of negative 4. Momentum in this context is 9.5 times 10 to the power of negative 28. So let's see that how. 700 706.63 times 10 to negative 34 divided by 9.5 times 10 to negative 28. You have 6.97, approximately 700 times 10 to negative 9. Yes, it's between this range, so So it's red light. The next question. A beam of red light. This is the intensity. Incident on this plane. The momentum of each photon in the beam is this. So the beam of red light, if it incident on this plane, most likely is going to reflect, change direction. So there will be change in momentum in this case. So there will be change in momentum, so which is like 2p or so. Sorry, I don't know what they're trying to say. All of the red light reflected. Oh, you said it. All of the red light reflected by the mirror in opposite direction, in original. The cross-sectional area of the beam is 2.5 times 10 to the power 6. You are given intensity, you are given momentum, and you are given area. Intensity, momentum, and area is given. Momentum and area is given. Show that the number of photons incident on the mirror per unit time is this. This is what you want to show. What you want to show, the unit is per second. That's number of photons per unit time. Per second is 1 over t. Okay. Now, let me work towards what they asked us to show. So in this case, since what I want to show is like per second 1 over t. Remember that power is energy over time. So energy is power times time. So energy is power times time. Energy over power is equal to time. What I want to do is 1 over t. 1 over t should give me power over what? Energy will give me 1 over t. Maybe times n, number of what you want me to do, number of stuff per unit time. So that should be power over energy. Now, remember we are given intensity. This intensity is power over area. So power is intensity times area. That's power. My power in this question is intensity times area. Equation 1. At the same time, I have to find power. How about energy? I think energy can be, look at the first, what I did here. What's energy? Momentum multiplied by speed of light. Yeah. So energy can be momentum times speed of light. So let's do that. So number per unit time is equal to power by energy. Power is intensity times area. Energy is momentum. This is momentum multiplied by speed of light. So number of mirror per unit time. Intensity is 160. Check the question. Area is 2.5 times 10 to the power of negative 6. Momentum we are given as 9.5 times 10 to the power of negative 28. Speed of light 3 times 10 to the power 8. So the number per unit time. Let's check my calculator. 160 times 2.5 times 10 to the power of negative 6 divided by 9.5 times 10 to the power of negative 28 times 3 times 10 to the power of 8. Yes, we got it. We have 1.4 times 10 raised to the power 15 per second. This is what they asked us to put. Use the information in B1 to determine the pressure exerted by the beam. Remember that on the beam, like I said, on the beam, the pressure is force over area. What is force? Rate of change of momentum. So it's reflected back. The rate of change of momentum, 1 over change in time. So force. So what's the change in momentum? We check it. I put 2p. Easy. We go with this, come to the other side. So change in momentum with 2p. So 2p, that's 2 times momentum is 9.5 times 10 to the negative 28. And this 1 over time is this number of units per unit time. 1.4 times 10 to the power 15. That's our force. So now this is force. This is our force. Pressure is force over area. So force is 2 times 9.5 times 10 to the negative 28 times 1.4 times 10 to the power 15 over area. The area is 2.5 times 10 to the power negative 6. So let's punch our calculator. 1.1 times 10 to the power negative 6 Pascal. That's the pressure. C question. The beam of red light in B is now replaced with blue light. Remember, Roy is now replaced with blue light. And blue light wavelength is between 450 and 495 nanometer. Remember, I said red light is between 650 to 750, 650 to 750, 620 to 750 nanometer. So the wavelength of blue light is smaller. And the wavelength of blue light is smaller. Energy is equal to hc over lambda. So energy is in so smaller wavelength, bigger energy. And with another formula, I said energy is momentum times speed of light. So bigger energy give bigger photons. So bigger momentum, bigger energy, bigger momentum. And lambda is equal to h over momentum. So obviously bigger momentum, smaller wavelength. That part has been stated anyway. And at the same time, I have um, number of, look at my formula here, power over energy. Number per unit time is power over energy. Energy is momentum times speed of light. So number per unit time, and okay, let's do it like this. Let me do it like this. beam of red light is replaced by blue light of the same intensity. Suggest and estimate that the pressure exerted on the mirror by the beam of blue light is less than, same, greater than the pressure of the beam of red light. Let's start like this. Since energy is inversely proportional to wavelength, so low wavelength because of space, low wavelength, high energy. And from this formula, momentum equal to energy over speed of light. So since there's high energy, obviously high photon momentum. I don't think I need this. So we have high energy, so we have high photon momentum. High photon momentum. So high photon momentum, look at the formula here. Number per unit time is power over momentum multiplied by speed of light. High photon momentum, lower this. You can see it from this formula. High photon momentum, fewer number of photons, photons. Hence, approximately same pressure. Yes, same pressure because fewer number of photons are now emitted, so it can be lower pressure due to the high photon momentum. That will be the same pressure. That's it. What is meant by nuclear fusion? Okay, this is um, this is this is when two light nuclei combine together or join together to form a larger nucleus, of more stability, with the release of energy. Sketch the variation of binding energy per nucleon V over A for 1 to 50. Okay, so it's like this. Binding energy is always increasing as the atomic number increases. The point looks like this. The element with the highest binding energy is iron 56. A is 56, 26 iron. That's A. The highest. Let's get it wrong. I messed it up again. something like this. Something like this. Yes, it's there. For it, not satisfied with this diagram. Get it? But supposed to be very okay like this. Iron, the mass number 56 has the highest binding energy per meter. So binding energy increases from 56 downwards are unstable element. This is the graph. So a point X that could represent a nucleus that undergo alpha decay. Alpha decay which means it's decaying to become stable. So from this graph, let me show you something from this graph. This side, from year to year, going in this direction is fission. Fission. In this direction is fusion. So element decay to become stable. Stability is around this region, from A to 0, stability in a region. So any element down to become stable must move towards that side. So if this is A here, so if an element undergoes decay, it's most likely around this region. So a point X that represents a nucleus that undergoes decay. So this element in this region are the one that are possible to decay just to form stability. The second one, a point Y that represents fusion. Okay, fusion, they can't fuse to go downward because stability is going upward. When they fuse, is to attain more stability. So it's around Y, this way, in this direction. So Y could be that region. So D question. According to a nucleus Z undergoes nuclear fusion to form strontium-93 and xenon-139. Okay, they undergo nucleus fusion. Okay, so 1 mole of Z releases 1.77 times 10 to 13 joules of energy. So 1 mole releases that. Okay, the fact that 1 mole of Z gives us 1.77 times 10 to 13 joule. One more give us this times 10 to the power 13 joule. Now, which means that I remember that 1 mole of any atom contains 6.02 times 10 to the power 1 mole of any substance contains 6.02 times 10 to the power 3 atoms, which is 1.77 times 10 to the power 13. We are talking about just one atom of Z. So one atom of Z will be 1.77 times 10 to the power 13 divided by 6.02 times 10 to the power 23. This one is in joule. So 1 atom of Z will give us 2.94 times 10 to the power minus 11 joule. This is 1 atom of Z produced this. So the question said the fission of 1 mole of Z releases this energy. So 1 atom of Z, this is the energy released. Determine the energy per million. Determine the energy per what? Million. So to get the energy per million, now, so binding energy release, the formula for energy release is always binding energy. Energy release is always binding energy of the product. That will be anyway. The fact that the binding energy of strontium and xenon, the sum, is greater than the energy release. So energy release will be binding energy of strontium plus binding energy. What I'm trying to say is that the total binding energy of strontium and xenon is greater than the binding energy of Z. The total binding energy of this strontium and xenon will be greater than the binding energy of Z. So energy release will be binding energy of strontium plus binding energy of xenon minus binding energy of Z. So we are looking for binding energy of Z. So the binding energy of Z will be binding energy of strontium plus binding energy of xenon minus binding energy, minus energy release. Minus energy release. So binding energy of Z will be, what's binding energy of strontium in the question? 1.25. Xenon 1.81. They have the same power, times 10 to the minus 10. Energy release is 2.94 times 10 to the negative 11. So binding energy of Z from our calculation will give us 2.77 times 10 to the minus 10 joule. But the question asks us to find binding energy per nucleon. So let's get the nucleon number of Z. Let's get the nucleon number of Z. So the nucleon number of Z most likely will be 93 plus 139 plus 2, 2 times 1, 2 minus, this is X. So Z is X. From here, 1 plus X equal to 93 plus 139 plus 2. So X will be 93 plus 139 plus 2 minus 1. So X will give us 233. That's the nucleon number of Z. So N, nucleon number of Z is 233. So binding energy per nucleon of Z, so will be 2.77 times 10 to the power of negative 7 all over 233. So that will give me, the question in mega EV. Remember that 1 EV is 1.6 times 10 to the power of negative 19. 1 mega EV is 1.6 times 10 to the power of negative 19 times mega is 10 to the power 6. So 1 mega EV is 1.6 times 10 to the power of negative 13. So if 1 mega EV is 1.6 times 10 to the power of negative 13, so X, I want to get 2.77 7 times 10 to the power of negative 10. This is my binding energy. We want to get it in mega EV, which is X. Cross multiply to V. So in this case, X will be 2.77 times 10 to minus 10 over. So literally to convert my 2.77 times 10 to minus 10 to mega EV, I have to divide by 1.6 times 10 to the power of minus 13. So let me go back. So um, so my binding energy to convert to EV, that's 2.77 times 10 to minus 10 all over 1.6 times 10 to the power negative 13. So binding energy per Newton now be 2.77 times 10 to the power negative 13 over 1.6 times 10 to the power minus 13 multiplied by 233 and do the max arrangement to give us 7.43 mega EV. I believe it's clear. Number 10, in the last question. So ultrasound and X-ray are both used in medical diagnosis to form images of internal structure. Complete the following method of production. Okay. Um, ultrasound. How is ultrasound produced? Okay. Short word, applying, alternating PD across the crystal or piezoelectric crystal, applying alternating PD across the crystal causes or lead to vibration. Lead to the vibration of the quartz crystal. The same thing. The short way or the short summary of it. X-rays are produced by the acceleration of fast moving electrons. Fast moving electrons hitting the metal target. When they hit the metal target, they decelerate and X-rays are formed or produced. How are they detected? Now, reflected ultrasound, reflected ultrasound from the structure, reflected ultrasound from the structure, incident on the transducer, which acts as the or as detector, I'm going to teach this topic very soon. They are just asking us to summarize it. For X-rays, detected wave, absorbed, reflected, and transmitted. For X-ray, it's transmitted. We don't have time to talk much about it. I'm dropping the topic soon. That's it. For one type of wave passing through the tissue, 72% of its initial intensity. The wave, for one type of wave passing through the tissue, the wave has 72% of its initial intensity. The incident, after it's passed through thickness of 6.2 centimeters, calculate the linear attenuation coefficient. So I equal to I naught e raised to the power minus mu x. Linear attenuation coefficient is mu. I remember they said 72% of initial intensity is transmitted. So 72% is 0.72 of I naught is transmitted. So I over I naught is equal to 0.72. So from here, I over I naught equal to e raised to the power minus mu x. I over I naught is 0.72 equal to this. So we have an exponential function. In that case, we take the lane of both sides. Lane of 0.72 equal to lane of e raised to the power minus mu x. So lane of 0.72 from the law of lane or logarithms, mu x shoots to the back, we call lane e. We have a law, lane e is 1, because lane e is the same thing as logarithms of base e to e, which is equal to 1. So at the end of the day, we have lane 0.72 equal to mu x, and x is 6.2 meter, 6.2 centimeter, sorry. At the end of the day, negative mu equal to lane 0.72 over 6.2. So lane 0.72 divided by 6.2. We have negative, we have this equal to negative 0.053. Negative cancel negative, so this is 0.053. That's it. Last question in this paper. Another wave of the same type as in B passes through 9.3 centimeter of the same tissue. Calculate the percentage of initial intensity of the wave that is attenuated. The percentage of the initial intensity that is attenuated, I over I naught. How you are looking for? So since I equal to I naught, e raised to the power this is what you are looking for, the percentage that is attenuated. Now this is the ratio of the ratio of transmitted over the original. This is it. So the ratio of transmitted over the original is e to negative, because it's the same tissue, they have the same mu 0.053. X is now 9.3 centimeters. So I over I naught will give us e to the negative of 0.053 times 9.3. We have, so the percentage times 100, we have 61%. This is the one that is transmitted. The one that is attenuated will be 100 minus 61%. That gives us 39%. That's it. I'll see you tomorrow for paper 4 variants.